Hey, college physics students. This is the static coefficient of friction lab. You know, this relationship between the frictional force and the normal force is not a law of nature. It's a simple approximation to a very complicated situation. Friction's a very ubiquitous force. It's all around us. We couldn't walk without it, by the way. It pushes us forward when we're walking. Just imagine trying to walk on a totally frictionless surface. You won't go anywhere. Anyway, so it's an important force. But this relationship with the coefficient of today's static friction is not a law of nature. It's not really it's not really as reliable as it's treated out in the industry. So part of the reason for this lab is to make that clear to you. Okay, so what do we need? My camera going here. Need our safety glasses. My connection is a little slow today. Need our safety glasses. We need some paper clips, some big paper clips, little paper clips. We need our block of wood with some kind of hook in it. So a 6 to 8 inch long 2x4. And here's our safety glasses. Let's get those on. We need our force probe, 0 to 10 newtons. So let's get started. Okay, the first thing we're going to do is get some water. We also need these empty water bottles, Gatorade bottles in my case. Let me get another pair of glasses here. I might need these big magnifying glasses. Okay, better. So we need our force probe, 0 to 10 newtons. As I pointed out, we have to be careful with this. Okay, so the first thing we want to do is put some water in these water bottles and make a 2 Newton weight, a 4 Newton weight, and a 6 Newton weight. And I'm also going to make a 3 Newton weight. We don't need it for this lab, but we might later on. So let me see. There's about 100 grams has a weight of about a Newton. And there's 30 grams in an ounce of water. So we need about 3 1/3 ounces for a Newton. So that means I need to make 2 Newtons, I want to make my 2 Newton weight here first. To make 2 Newtons, I need about 7 ounces. This is a 12 ounce container, I believe. So I'm going to fill it a little bit more than halfway. There we go. I've written 2 Newtons on this because we're going to need these weights later on. So now I'm going to take a paper clip. I can probably get by with a little paper clip in this case. I'm going to take a paper clip, and any water bottle has this little ring around it where the lid used to be attached. And I'm just going to hook a paper clip in there so I have a hook on it. And then I'm going to put the cap on, and I'm going to use my force probe to see how much it weighs. I'm going to probably need more light here. it's saying, 2.6 newtons. So I got a little too much water in here. Pour a little bit of it out. .3 newtons. You get the idea. Might want to do this by the sink. It'd be a little bit easier, I think. You want to hold the force probe very steady. 2.2 newtons. Two newtons on the button. Well, I've already made a 3 newton. Oh no, it's empty. I'll make that later. Here's a 4 newton that I've already made. Let me double check it here. Four newtons. That I had to use a 12-ounce bottle for, I guess. No, this is 20 ounces. I had to use a 20-ounce bottle because 4 newtons is going to be 4 times 3.5 is about 13 or 14 ounces to get 4 newtons. So there's a 2 newton and a 4 newton. Here is a big bottle I might be able to use for a 6 newton. This is 34 ounces. So let me see. 6 newtons is going to be over 20 ounces. So I'm going to need quite a bit more water here. I'm going to need a pretty strong paper clip for this too, because we're getting up to be around a pound, more than a pound. 6 newtons is more than a pound. I really don't want to go above about 8 newtons on the force probes until we get to the end of the semester. And this one does not have a good ring on it. Hope it's strong enough. Okay, so I got my big paper clip there. Put the lid on. Let's see how much it weighs. I'm looking for 6 newtons. Ooh, 7 newtons. Too much. So I got to pour quite a bit out of this, like 3.5 ounces out of it. See what we're down to. Oh, you know. Oh man, hot dog, 6 newtons. So I'm going to write 6 newtons on this. All right, bingo. And that's the beginning. So we got a 2 newton weight, a 4 newton weight, and a 6 newton weight. Now, the next thing I'm going to do is weigh my block. So, easy enough. .3 newtons. 3.3 newtons. I'm going to write that on my block. 3.3 newtons. All right, now let's begin the experiment. Here's what we got to do. We're looking for two quantities here, the normal force and the frictional force, the static frictional force. The static frictional force can take on any value, can resist any value up to a certain maximum value, and that maximum value is what determines the coefficient of static friction. So I'm going to set my, oh, we also need, I forgot to mention my, my wood plank here. The same plank that I've been using for a ramp. So here's what you want to do. You want to arrange this so you can see the scale. And you want to gradually pull. You want to pull horizontally. You don't want to pull at any kind of angle like this because you'll be lifting the surfaces and reducing the frictional force. So let's stop for a minute. Okay, the block is sitting here. There's a normal force on the block in this direction exerted by this. And that's the normal force that goes in the formula for the coefficient of friction. And if I start pulling on this, there's a static frictional force in this direction, resisting it. But it will only resist it up to a certain point, and that's the point I want to find. That's the frictional force I want to find. So I'm going to pull this horizontally until it just starts slowly increasing the force until it just starts to move. 0.9 newtons. So, with a normal force of 3.3 newtons, that's the weight of this, the static frictional force maximum is about 0.9 newtons. But I want you to take a couple of readings. Move the block around on your surface. Here I'm getting about 1.1 newtons. Remember, each of those little divisions on the scale is 0.2 newtons. So I'll do it over here. I'm getting 1 newton. So with a normal force of 3.3, I got 3 values for the static frictional force, the maximum static frictional force. And I'd write those down. I want to take 3 readings for each normal force. Okay, now I'm going to set this 2 Newton weight on top of the block. Now the normal force is 5.3 newtons because it's the weight of this block plus this 2 newtons that I set on top of it. So now the normal force is bigger and the maximum static frictional force is going to be bigger also. And I want to measure it, once again, 3 times in 3 different places. I'm getting about 2 newtons there. I'm getting 1.8 newton there. And I got 2 newtons there. All right? Now I'm going to take a 4 Newton weight and set it on top of this. Now my normal force is, let me see, 4 plus 3.3. Now my normal force is 7.3. We'll see what the I'm getting about 2.8 newtons. So you get the idea. You do 3 measurements with this 4 Newton weight on there. So that's 4 plus 3.3. Then you take your 6 Newton weight and you do it again. So then you take your 6 Newton weight and your 2 Newton weight and put them both on there. That makes a normal force of 9 plus 3.3. So then you take your 6 Newton weight and your 4 Newton weight and put them both on there. That gives you 10 plus 3.3. Let me make sure I don't get, let me see how big this force is. This force is going to get pretty big. Yeah, it's less than 8 newtons though. Okay, so you should have six sets of three measurements each. And that's your data. Then you're going to make a graph of frictional force on the y-axis and normal force on the x-axis, the horizontal axis. And the slope of that graph, it should be close to a straight line, the slope of that graph will be the coefficient of static friction, as explained in the lab write-up. All right, now there's a part 2, which is easy enough. And this analysis is in your book, I think. If not, you can ask me about it. But if you start raising this ramp, the block will eventually slide. And the angle at which it's, the tangent of the angle that it begins to slide is given by the static coefficient of friction between the block and the table. So, for this you're going to take your inclinometer see if I can get it going on my phone here. Inclinometer. I think it's still on here. There it is. You're going to take your inclinometer and set it on the end of the board. And start raising the board. About 27 degrees. So you need to take 3 measurements of this as well. Move it to a different place on the board. "21 degrees that time. "25 degrees that time. Okay, then you're going to try the same experiment with the block sitting like this, vertically. About 20 degrees. Try it over here. You can put it anywhere on the board. About 25 degrees. And you take 3 readings like that. Now the interesting thing about that is that the static frictional force does not depend on the area. So I have just as much static frictional force with a block sitting on its narrow side like this as I do with the block sitting on its flat side like this. Something that's kind of counterintuitive. Anyway, so that's your lab.